January 17, 1995, 5:46 in the morning. The ocean floor beneath the Akashi Strait ruptures. In less than 20 seconds, more than 6,000 people will die. And directly above the epicenter stand two steel piers, nearly 300 meters tall. They are supposed to support the longest bridge in human history. The tremors subside. Engineers rush to the site, expecting to see a heap of twisted metal. But the piers are still standing, intact. Only something has changed. The bridge has become longer. Now look what actually happened here. The Akashi Strait, 4 kilometers of open water between Kobe and Awaji Island. On the map, it looks like a short crossing. In reality, it's one of the most hostile places on Earth for any construction project. Currents rush here at 4.5 meters per second. Such a current would sweep a person away instantly. The seabed drops down to 110 meters. Typhoons arrive every year. And underneath all this lies one of the most active seismic zones on the planet. And that's not all. More than 1,000 ships pass through the strait every day. It's one of the busiest shipping lanes in the world. A bridge can't be built just anywhere. Block the channel and you stop global shipping. And people have already died here. 1945. A ferry sinks in a storm. 304 dead. 1955. 2 more ferries sink in the same disaster. 168 dead, many of them schoolchildren. People take to the streets. Stop drowning people in the strait. Build a bridge. But there's one problem. A bridge of this length doesn't exist anywhere in the world. And here's what's important to understand. This bridge wasn't built for decades. Not because they didn't want to, but because they couldn't.
Imagine standing right here on this very shore. The water looks calm on a good day, but underneath, the currents are moving like a highway. Building a bridge over this? In the 20th century, it was suicide.
In 1961, the Japanese commissioned an engineering study. 6 years later, the scientists delivered their verdict. Literally, the conditions for this bridge are so severe that there are simply no comparable long-span structures anywhere in the world. Simply put, no one has ever built like this before. And it's unclear whether it's even possible. It would take 20 years from the first drawings to the first stone. 20 years of calculations before the first car is driven into the seabed. Here's the engineering challenge. The law requires a clear channel width of 1,500 meters. Otherwise, you'll block shipping. This means the main span, the distance between the two supports, must be closer to 2 kilometers. You might be wondering, how much is that anyway? Here's a figure. That's 40% longer than any suspension bridge ever built on Earth. Not 5%, 40. For comparison, that's almost 1.5 times longer than the famous Golden Gate Bridge in San Francisco. And now the numbers themselves. The total length is 3,911 meters. 2 supports are almost 300 meters high. It's like Tokyo Tower placed directly into the sea. And this entire colossus must withstand winds of 290 kilometers per hour and an earthquake of magnitude 8.5. On paper, it's madness. All that remained was to build it, and immediately a question arises. Why a suspension bridge, and not a regular one with piers? The answer is simple. You can't put a pier in the middle of the strait. It would block the fairway and become a target for ships. So, there has to be a void between the two towers. 2 kilometers of void. And only one type of bridge can span such a gap. A suspension bridge.
A 2-kilometer empty void held by nothing but steel wires. If even one calculation is off, the physics of wind will twist this massive road. The engineers were stepping into completely uncharted territory.
The entire road hangs from cables slung over the towers. There's no other option. The engineers have no choice. But before laying a single stone, engineers must be sure the piers will withstand the wind. How can they test this before the bridge is even built? Here's the solution. They build 2 scaled-down replicas of the piers, 100%, and then they run them through a wind tunnel. Wind, storms, gusts, everything just like in the real strait, only in miniature. The model holds up. That means they can build the real thing. Not a single mistake at this stage. A mistake here means a collapse later. It all starts at the bottom, and the bottom is 60 meters underwater in a current that carries a person away. How do you put a foundation where you can't even stand? Here's the solution. Engineers assembled giant steel cylinders, 80 meters in diameter. That's the width of a football field standing upright. But first, the bottom needs to be prepared. Divers and equipment clear and level the area at a depth of nearly 50 meters, where the water presses and the current rushes. Only then is the cylinder lowered. Precision is critical.
Miss the mark, and the entire support will tilt. And the tilt of a tower as tall as a skyscraper can no longer be corrected. But now comes the main trick. Ordinary concrete in such water would simply be washed away by the current, and there would be no foundation. That's why engineers create special underwater concrete. It doesn't wash away. It sets right in the water and fills the cylinder from the inside. Simple. Brilliant. The foundation stands. But the current doesn't go away. It will begin to wash away the soil from under the support, and sooner or later it will subside. That's why they pour a protective belt of stone around the foundation. The current hits the stone, not the support. Another problem solved. Meanwhile, on the shore, they're digging trenches for the anchors. These are the blocks that will support the main cables of the entire bridge. One such pit extends 64 meters below sea level. More than 260,000 cubic meters of concrete are being poured into it. Each anchor weighs 350,000 tons. 350,000 tons of concrete just to hold the ends of the two cables. The foundations alone are a mega project. Now imagine the scale of coordination. More than 100 contractors are working on the bridge simultaneously. Each is responsible for their own section. If even one makes a mistake, the entire bridge will be weakened. And all this is not a standalone project. The Akashi Kaikyō is just one link in a gigantic plan that connects Japan's main islands with bridges across an inland sea. 6 lanes of traffic, hundreds of companies, one plan, and everything depends on no one failing. And here's what makes the task even more insane. The strait can't be closed. While construction is underway, more than 1,000 ships continue to pass through it every day. Enormous cargo ships pass right between the supports under construction. A crane error, a slipped load, a miscalculation, and it's no longer just a construction accident, it's a catastrophe in the middle of one of the planet's main shipping lanes. Engineers are building a gigantic bridge right in a living, moving stream, without stopping it for a single day. Now the supports grow skyward, but the tall, slender support has a hidden enemy, the wind. A gust sways it rhythmically. The swaying grows on its own, and if it's not stopped, the steel will break. Watch how they fix it. Heavy weights are suspended inside the supports, tuned mass dampers. The support sways to the left, the weight shifts to the right. The support to the right, the weight shifts to the left. It constantly strikes out of phase and dampens the oscillation before it has a chance to grow. The movement is nipped in the bud. The crisis is over. By early 1995, both supports were ready. The canvas hadn't been hung yet. And then the Earth began to move. The Hanshin earthquake, magnitude 6 and 9. The epicenter is almost exactly between the two piers. Think about it. Nature strikes at the weakest point of the construction, at the worst possible moment, years ahead of schedule. This is the ultimate test, one for which no one prepared. Engineers check the piers, and this is what they find. The steel is intact, not a single crack in the structure. But the earth itself shifted. The two piers were pushed apart almost a meter. Forever. That's what's truly crazy here. The engineers didn't tear anything down, they simply recalculated the design. The main span, originally planned for 1,990 meters, became 1,991. The earthquake didn't break the bridge, it extended it by exactly 1 meter. And remember this detail. The earthquake that killed 6,000 people and leveled entire neighborhoods of Kobe couldn't leave a single crack in these unfinished supports. That's what good engineering means.
You don't argue with the elements. You design so that the elements lose. Construction was halted, of course, but only for a month. While all of Kobe was clearing away the rubble and burying the dead, the engineers double-checked every detail of their design. They were convinced the structure held up, and so the work continued. That month was the only delay the bridge suffered in its 10-year construction. The earthquake didn't knock a single day off the schedule. The bridge was completed on time. Now they have to literally suspend 2 kilometers of road in mid-air. The entire track is held up by 2 main cables, and this is what's inside each one. 36,830 individual wires. Each one is thinner than a pencil. They are twisted into a single cable a meter thick. But how do you stretch the cable across the strait, where not a single support will stand? Through the air. First, narrow safety bridges are stretched between the towers. Workers will walk along them at a height of almost 300 meters above the strait. Then they begin the process. A special trolley pushes a thin strand of wire back and forth, from bank to bank, over and over again. Thousands of passes. Coil after coil, the cable grows directly in the air above the water. Not a single wire can sag any differently than it should. Otherwise, the load will be distributed unevenly, and the cable will begin to wear out prematurely. Now lay all this wire in a single line. 300,000 kilometers of steel. That's enough to wrap around the entire planet almost 8 times. 8 times around the Earth, in a single bridge.
8 times around the Earth. A mind-blowing scale. But this steel giant has a silent, invisible killer.
Rust. Moisture will seep into the cables, corrode the wires, and the bridge will begin to die from the inside, where no one will see. The solution still works today. Dry air is blown through the cables. It forces the moisture out.
Quietly, constantly, for decades. Right now, as you watch this video, dry air is breathing inside the bridge, keeping the rust out.
If these pumps stop even for a few days, the ocean's salt will start eating the steel from within, where no one can see it.
The cables are taut. Now they raise the bridge deck, section by section, suspended from the cables above. But a flat road 2 kilometers long is like a giant sail. And then the engineers remember a terrible lesson. Once in America, a suspension bridge caught the wind in resonance. The deck began to twist more and more, and before everyone's eyes, it collapsed into the water. No one was going to make the same mistake again. That's why the deck here is not made solid. A double-hinged truss, an open steel lattice. The wind passes right through it without encountering a solid wall. The deck bends, but does not tear. The sail has been turned into a sieve. Problem solved. And here it is, the moment of truth. When the first section of the bridge deck rests on the cables, the bridge bears its own weight for the first time. Everything that had previously existed only in calculations is now tested in reality. The cables tighten. The supports bear the load. 20 years of drawings, 10 years of construction, everything comes together at this point. And the structure holds, exactly as calculated years before. And here's another detail that almost no one thinks about. Metal expands in the heat. And here, there's 4 kilometers of metal. On a hot day, this bridge expands. How much? Up to 2 meters in a single day. 2 meters. The bridge literally breathes with the weather,
stretching during the day and contracting at night.
2 meters. If this bridge were completely rigid, the heat would simply bend and break the steel. But look how they solved it.
And the entire structure is designed to accommodate this movement without cracking. Not a single joint should jam. The bridge is alive, and it's built into the plans. And all this costs money. How much? About 500 billion yen, about $5 billion. At the time of its opening, it was the most expensive bridge ever built.
But for that money, Japan got more than just a crossing. It got proof that the impossible can be built. On April 5, 1998, the Akashi Kaikyō Bridge opened. At that moment, it became the longest suspension bridge on Earth. It held this record for 24 years. Only in 2022 did the Çanakkale Bridge in Turkey finally surpass it. But only by a few dozen meters, and only because Japanese engineers were the first to prove it was even possible.
Records are meant to be broken. But the true legacy of this bridge isn't just its size. It's what happens when the sun goes down.
Now look at it at night. The Japanese call it the Pearl Bridge. Nearly 2,000 lights run along the cables, changing colors all night long. 1,737 lamps, each one in its place. 20 years of design, 10 years of construction, an earthquake that would have stopped almost any other project on the planet. And it stands. Every day, about 23,000 cars cross it.
23,000 cars. Think about that number. Every single day, thousands of lives pass over this deep water in complete safety.
23,000, across a strait that once swallowed ships whole, along with their people. And tests continued even after the bridge opened. Since then, dozens of typhoons have passed through the bridge. Wind, rain, storms, everything that should have toppled it, but it never did. Calculations made in the wind tunnel at a scale of 100 proved accurate in the real world, at full scale, under a real typhoon. The engineers guessed everything. And think about what's changed for ordinary people. Previously, to cross this strait, people would board a ferry and hope there wouldn't be a storm. Every crossing was a small risk. It was on such ferries that those 304 people died and those 168. Today, the same journey takes just minutes. You're driving high above the water and don't even think about the waves below. The danger that once claimed lives has simply disappeared. Engineers have erased it. That's the whole point. The strait that twice sank ferries carrying children no longer kills anyone.
Engineers didn't conquer the sea by force. They outsmarted it. Current, wind, earthquake. Each threat was taken apart and neutralized one by one, bolt by bolt, calculation by calculation. But a bridge is just the beginning. What if the land you need to build on doesn't yet exist? And the second you create it, it begins to sink into the sea.
Imagine trying to build a multi-billion-dollar airport where there is literally nothing but water, and watching it sink every single day.
An entire airport built on an artificial island, man-made in the middle of the sea. An island several kilometers across. And it's been sinking from day one. Not ever. Right now, while planes are landing on it. The engineers knew it would sink even before they laid the first stone, and they built it anyway. And now they fight every day to keep it afloat. How do you keep something above water that, by all the laws of physics, should sink? That's for next time. If you are interested in how man outplays the elements, subscribe. We only discuss stories like this here. See you at the next impossible structure.